In these sets of notes, we're going to talk about inductive reasoning. So inductive reasoning means that we are making a conclusion based on the observations and patterns that we notice. Conjecture is a big one we're going to hear a lot about. And a conjecture is a concluding statement reached using inductive reasoning. So you use inductive reasoning to make that conclusion. So how we're going to work out these different examples, we're not going to do every one together, but I will give you some of the answers if we don't do it together. So on this first one, we need to find the next 5 terms of the sequences, or the sequence that's given to us, and then write a conjecture. So we need to use our deductive or inductive reasoning right here to make the conjecture. So when it says to make a conjecture, then that implies that we need to use inductive reasoning to do that. So we need to notice the pattern and observation. So we use our observation of what's happening with this and notice what the pattern is to make that conjecture. So what you have to do with different patterns is you have to check a couple different things. So it could be added, it could be multiplied, it could be any different things between the different terms. You want to look at, okay, how do you get 38 to 31? How do you get from 31 to 24? How do we get from 24 to 17? And we notice that they are all decreasing, so then check to see how much. So this one is decreasing by 7. 31 to 24 is also decreasing by 7. If we continue that, we also get the 17, so we can assume then, or make our inductive reasoning, so using inductive reasoning, we can make a conjecture that it is subtracting by 7 each time to reach the next term. That means if we subtract by 7 after 17, so 17 minus 7 gives us a 10. If we subtract 7 more, that gives us a positive 3. Subtract 7 and we get a negative 4. Subtract 7 again and we get negative 11. Subtract 7 and we get a negative 18. So on this one we found the next 5 terms in our sequence, plus we made a conjecture, so it's our concluding statement that explains the pattern by using our inductive reasoning. And number 5, I would like you now to fill in what the next 5 numbers in the sequence are, so you have to notice what the pattern is, and then describe what that pattern is and make that concluding statement or our conjecture. What you should have noticed then is that it is adding 25 minutes each time. So it's a little bit easier to notice that between our 30 to 55. So it's adding 25 minutes. So if we do that with our 8:20, you get 8:45. And then you get 9:10, 9:35, 10 o'clock, and 10:25 is what you should have filled in. Then explaining what that looks like. We could say to generate the next term, take the previous time and add 25 minutes. Here is the answer for number 2 if you would like to copy that down. So go ahead, push pause, and then after a few seconds, each following problem will show up. Here's your answer for number 3, and if you notice, one thing that I want to point out here for you is when it says that each element is a square of the natural numbers, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and on. So you're kind of your counting numbers. So to generate the nth term, what that means is that you notice that this is the 9th term, so you square 9. So if we wanted the 10th term, you would square 10, and you'd get 100 right there. Here's your answer for number 4. So the difference between them is you need to add 3 letters each time. So after the letter A, you have B, C, D. So that is the 3rd letter after the previous letter. This last one would be kind of tricky. And if you notice that each of the terms are part of digits of pi. So 3.141592653. So you would have to know which digit of pi you would want, and then that would determine what the next number would be in our list. The definition of counterexample is a really important one that you want to understand, and if you ever have questions on it, please, please, please ask me in class. So a counterexample is an example, so that's where the example part comes from, and the example shows a conjecture is false. So remember, on your previous page of your notes, you were writing conjecture. So you're determining what the pattern is and then describing it. So if your pattern was wrong, then an example, a counterexample, would be an example, so a next number in the term that would prove that your solution or your reasoning was not correct. So you're proving someone that what their assumptions are that is false. So in these first ones, we want to determine whether the conjecture is true or false. And if it's false, we need to provide that counterexample. All right, we're going to jump around on this one as well. So we're going to do number 3 together first. So the product of 2 perfect squares is always a perfect square. So they're saying if we multiply 2 perfect squares together, then it will always equal another perfect square. So let's try it out. So if we take 1, because 1 is 1 squared, is 1, and all right, so I'd pause that for a second. You can add in, those are just some other perfect squares, so some ones that we can work with. So if we take 1 times 4, that gives us 4. That one works because it equals another perfect square. If we take 9 times 16, that gives us 144, and guess what? That is a perfect square. That's 12 squared. If we took, let's try 4 times 9, that gives us 36. That is a perfect square. And if you continue on, you would see that these all equal perfect squares. So we can't come up with one. So this conjecture would be true. So since it is true, then there's no counterexample that we can give. All right, next we're going to do number 6. So vertical angles are never complementary angles. Well, we need to remember what those vocab words mean as well. So my picture right there are my vertical angles. So remember, if they have 2 intersecting lines, our vertical angles are those ones that are exact opposite corners from each other. So there's a pair of vertical angles, and they're saying that they're never complementary. So remember, complementary means that they add up to equal 90 degrees. Okay, so is there any combination of 2 numbers that are exactly the same that could give us 90 degrees? And there is. If both of those were 45 and 45, then they would be complementary. So this would be false, because it's not always true, and because we have shown that if our 2 angles are 45 degrees in our picture right there, then they are complementary. So it proves this word right here that is never, cannot be the word that should be used. So our explanation, so provide a counterexample. So we can say it's false, but the whole explanation is the biggest part here. So if we have 2 angles that are 45 degrees that are vertical, like our picture right there, then they are complementary. So it proves that the second part of our sentence is not true. And number 10, now I would like you to try this one on your own. So tell me if it's true or false, and then put your answer off to the side. All right, squaring a number and adding 1 will always produce an even number. So this, what it equals then will always be an even number. So let's try some. So if we had, let's see, 5 squared gives us a 25, which then if we add 1, that gives us a 26. That is an even number. Okay, so that one works. But that was an odd number to begin with. So let's start with even. If we had 4 squared, that gives us 16. If I add 1, that equals 17. But is that always going to be an even number? No. So hopefully you put false, and then this could be my example, my counterexample right there. So put into more sentence form, we could say that 4 squared plus 1, so my even number, or my number squared plus 1 equals 17, which is not an even number. So these last 2, if you want to come to class with 2 of these filled out, that would be awesome, because then we can discuss those in class, and we can see if you guys came up with the correct or a conjecture, and then is it true or false with your counterexample.